A critical CNC machine is running at full capacity on a factory floor. The condition monitoring dashboard reports green across the board. Every operational parameter appears entirely normal. Then, the spindle suffers a sudden, catastrophic failure. To understand why the dashboard missed the breakdown, we have to look at the sensors themselves. The industry standard for machine health, dictated by ISO 10816 protocols, relies heavily on low-frequency vibration and temperature sensors. These two metrics are lagging indicators, designed to measure macroscopic physical shaking and severe heat accumulation. In a high-decibel industrial environment, ambient factory noise easily masks early, subtle vibrations. By the time a machine shakes violently enough to breach that noise floor, the internal tribological damage is already irreversible. We are measuring the autopsy, not the symptom. Current maintenance protocols do not predict machine failure. They confirm that terminal degradation has already occurred. The actual control point for predictive maintenance lies in a completely different frequency range, acoustic emission. AE sensors capture the microscopic sound waves generated by metal-on-metal shearing. Friction creates this high-frequency noise weeks before the metal physically displaces or vibrates. Capturing acoustic emission creates an immediate bandwidth problem. The sensor generates an overwhelming volume of raw, dense noise that easily chokes traditional analysis networks. The solution requires fusing acoustic emission streams with legacy vibration and temperature sensors to cross-verify signals. These inputs are then organized into a multidimensional graph data architecture. Interpreting this architecture requires a specific algorithm called a graph attention network, which mathematically maps the hidden physical couplings of mechanical degradation. To hear the silent, microscopic failures of heavy industry, we must shift from basic physical measurement to a complex, multidimensional data architecture. We can test the limits of individual sensors by establishing a strict physical baseline. In a controlled experiment, a super-precision 7014 AC angular contact ball bearing is intentionally run to failure by starving it of lubricating oil. The test rig tracks the bearing using 3 distinct inputs running simultaneously: temperature, vibration, and acoustic emission sensors. This chart tracks temperature against time. The line remains flat for 9,600 minutes, then spikes vertically. Adding low-frequency vibration yields similar results, energy registers just prior to the breaking point. Contrast those indicators with acoustic emission, showing significant friction anomalies thousands of minutes earlier. While AE provides early warning, relying on it in isolation creates a highly sensitive system prone to false positives, triggered by routine, transient load spikes. No individual sensor contains enough dimensionality to distinguish between a temporary operational anomaly and permanent oil film breakdown. Piping continuous acoustic emission and vibration waveforms to a central processor requires computational power that makes continuous monitoring economically unviable. We solve this raw data problem mathematically by extracting specific time frequency features from the waveforms using a Fast Fourier transform. This diagram shows how the Fast Fourier transform breaks down dense, chaotic waveforms into isolated mathematical features. We apply a strict filtering process to these peaks, discarding any features that do not show a clear, monotonic degradation trend over time. This rigorous filtering reduces massive industrial noise down to exactly 47 high-value features that strictly correlate to lubrication failure. To maintain a holistic view of the machine, these 47 features retain precise inputs from the acoustic emission, the triaxial vibration, and the temperature data. The features are then processed in a continuous sliding window of time, allowing the system to capture dynamic, real-time changes as the machine operates. Feature extraction transforms a paralyzing wall of data into a lightweight, highly concentrated stream of mechanical truth. To make these 47 isolated time series features actionable, we translate them into a spatial graph data structure. We represent the extracted features as 47 isolated dots, known as nodes, in 3D space. Each node holds sliding window data for a specific variable. The second component is the edges. Every node connects to every other node, creating a dense, fully connected web. These edges represent the complex mathematical relationships and the physical couplings between the different sensor features. Traditional time series analysis limits itself to observing variables in strict isolation. It analyzes a single data stream without context. Graph data inherently maps spatial dependencies. It perfectly mimics the physical reality of a multi-component machine interacting with itself under load. By mapping the machine's internal web, the graph structure tracks exactly how the friction of one component affects the health of all others. We process this massive web of relationships using a multivariate time series anomaly detection model driven by a graph attention network. The core function of this network is the attention mechanism. As the network trains on normal operational data, it learns to dynamically adjust the weight of the edges between specific nodes. Strongly correlated features group together into tight clusters, allowing the model to uncover hidden degradation patterns that simple thresholds miss. This rigorous learning process establishes a strict mathematical baseline of what normal, multi-sensor harmony looks like for that specific machine. The attention network learns the unique mechanical fingerprint of the healthy machine. Any tribological deviation becomes mathematically impossible to hide. Applying this graph data model to the physical CNC spindle test reveals a distinct return on investment. The graph network established the mathematical baseline for the healthy bearing, calculating a normal operating threshold anomaly score of exactly 0.31. This split timeline chart displays the exact moment of anomaly detection. On the top timeline, the graph network score crosses the danger threshold at 5,300 minutes. The bottom timeline shows the legacy temperature sensor registering the failure at 9,600 minutes, securing a 4,300-minute lead time. This 4,300-minute delta is the critical transition window. It separates the invisible onset of microscopic lubrication failure from irreversible physical burning. Securing this lead time empowers operators to perform localized restorative maintenance, entirely bypassing the need for emergency full system replacements. Fusing acoustic emissions with graph data successfully eliminates the element of surprise from industrial catastrophic failure. Deploying this architecture in a real-world industrial setting requires overcoming one final hurdle: the structural limitations of cloud computing. The current industry instinct is to pipe raw factory data to massive off-site deep learning models. For high-frequency signals, this is an expensive and dangerous distraction. Bandwidth costs and network latency make real-time continuous Fast Fourier Transform processing in the cloud impossible for acoustic emissions. The ultimate architecture required for deployment is Edge AI. True predictive maintenance relies on concealed complexity, running the cognitive engine inside the sensor housing itself. Industrial resolution depends on localized compute. By processing physical realities at the edge, the system maintains a silent watch, delivering only the exact, actionable truth to the operator.